A 10-gram arrow is traveling at 400 meters per second towards a 10-kilogram, 1 meter wide door. Okay, let's draw what that looks like. So here's my door, but I'm viewing it from the top, okay? And so I've got an arrow, which is 10 kilograms. I'll just draw it as a vector kind of arrow here. So this is 10 grams, sorry. 10 grams, and my door is 10 kilograms. Okay, so the arrow collides and hits the door. Okay, it hits the door at the edge, opposite the hinge, at an angle of 90 degrees. So it hits it on perpendicular to the surface of the door. The arrow gets stuck in the door and it causes it to swing closed. So let's say right now the door is open. This is the wall basically, like this. And then the door is going to swing and eventually it's going to close like that. So hopefully that makes sense to you. So I'm looking from above. Okay, what is the angular velocity of the door just after impact? So this omega, that's what we're looking for. Okay, so we have an arrow that's hitting the door. If the arrow and the door together is our system, we can say there's no net torque acting on the system. There's no other forces that are causing this door to swing. It's just the arrow hitting the door, and that's it. So because the net torque acting on the system is 0, we can say that the angular momentum of both the arrow and the door initially is equal to the angular momentum of the arrow and the door final, so after the collision. Okay, now this is another inelastic collision because the arrow gets stuck in the door. So let's think about what we're going to use for our formulas of angular momentum. So we have two different types of objects here. We have an arrow, which we're going to treat as though it's just a tiny little particle. Okay, and we have a door, which we're going to treat as a rigid body. And we're going to have to look at the table to figure out the moment of inertia of this door. Okay, so if we think about the angular momentum of this arrow right now, this arrow is about to collide into the door, so it does have angular momentum. It's going to make the door swing. So if we think about the equation, so the angular momentum for a particle is r mv sine beta, where beta is the angle between the r vector and the velocity vector. Okay, so when the particle is right about to hit the door, right here, the r vector is the vector that goes from the axis of rotation, which is the hinge of the door, to the particle. So that would look like that. That's the r vector. And the v vector is the direction that this particle is moving. So it's going this way. This is the v vector. So the angle between the r vector and the v vector is 90 degrees. So this beta is 90 degrees. Sine of 90 is 1. So this whole thing just becomes 1. So here we're talking about r of the door. So that's the width of the door. M is referring to the mass of the arrow, and V is the velocity of the arrow. Okay, so we just did the angular momentum for the arrow. Now onto the door. So when we find the angular velocity of a rigid body like this door, we're going to use the formula I, moment of inertia, of the door, times omega. Okay, is equal to the angular momentum of both of them together. So it's the same idea. The sine of beta is still going to be 90 degrees. The angular momentum of the arrow in the door, they're stuck together. So we can do this in a couple of ways. We can still treat them like they're two separate objects, or we can think of this equation as though it's exactly the same thing as I of the arrow, omega of the arrow. Does that make sense? I of an arrow, if we're treating the arrow like it's just a particle, well, I of a particle, the moment of inertia of a particle, is mr squared. And omega of a particle is v over r. And those r's will cancel out. And what do you have? mrv. It's the same formula. mrv or rmv. As long as the angle between the r vector and the v vector is 90 degrees, then the moment of inertia of a particle is mr squared, and your angular momentum is just going to be the same thing. You can think of it as moment of inertia is equal to mrv for a particle, or you could say it's equal to I times omega. It's the same. So on the right side, we can say is equal to the total angular momentum. So the total angular momentum would be the I of the part of the arrow plus the I of the door times omega final. And this is what we're looking for, this omega final. Okay. Now, initially, what do we know about the arrow? We know it's v. So it's nice that on the left side of the equation, we have the formula for angular momentum in terms of v over here. If we were to use a different formula that has an omega in it, we would just change the omega back to v by saying v equals omega r. Okay, so I'm going to clean this up a little bit. All right, so now we want to figure out what we're going to put in for the moment of inertia of the door, so I of the door. What are we putting in there? We're going to have to look at that table from the moment of inertia lecture. So here's the table. And we have to pick which picture would look like a door. Okay, so the door is a plane or a slab that has an axis of rotation about its edge, where the hinges are. So this would be the moment of inertia, 1/3 ma squared. So that's what I'm going to put in here. The moment of inertia of the door is equal to 1/3 ma squared. Okay. All right, so let's start to plug in the things that we know. So we have r, m of the arrow, v of the arrow initially, plus the I of the door is 1/3 mass of the door, a. So a from the picture is this distance of the door. Okay, it's the width of the door, squared times omega of the door is equal to I of the arrow. So the moment of inertia of an arrow is just mr squared plus I of the door, which is 1/3 ma squared times omega final. Okay, so now a and r from our picture is the same value. So we can just make all of them the same number. Okay, so if we want, we can make them all a's or all r's. It really doesn't matter. In the end, it's just the width of the door, which is this 1.00 meters. So this is my a value, or I could also say it's my r value. Okay, it's all the same thing. Okay, so we're trying to solve for omega final. So I'm going to think about what values do I know here. So my r, in this case, I'll write everything out on the side, is 1 meter. My mass of the arrow is 10 grams. I have to change that to kilograms, so 0.01 kilograms. My velocity of the arrow initially is 400 meters per second. My mass of the door is 10 kilograms. My A for the door, okay, so I'm talking about the width of the door, is still the 1 meter. Then when I have mr squared plus 1/3 ma squared, I really should have put subscripts there. So the IA is the mr squared, right? So that mass that we're talking about is referring to the mass of A. And the 1/3 ma squared, that's referring to the mass of the door. So ma, we already said, was 0.01. R is still 1. Mass of the door is still 10. A is also still 1. And then we're solving for this omega final. Okay, so I'm just going to rearrange the equation. Omega final equals R ma VA initial plus, before we plug this in, what is the angular velocity of the door initially before the collision? Before the arrow hit the door, what was its angular velocity? 0. It wasn't moving yet. So this thing is 0 and the whole term is gone. So let's just not put it in at all. And on the bottom, we have m, mass of the arrow, r squared, plus 1/3 mass of the door, a squared. Now I can plug everything in. So I have 1, 0.01, 400. Okay, I'm using all these values here on the left, over mass of the arrow, which is 0.01, r, which is 1 squared plus 1/3. Mass of the door is 10, a, which is 1 squared. Okay, so type this all up with me. And I get 1.196 radians per second. Okay, everything was in SI units, so our units for omega should be in SI units, radians per second. Okay, so now finally let's look at our significant figures. So in our question we have 3 significant figures. Here we only have 1 significant figure. Here we have 3, here we have 3, and that's it. So we have 3 significant figures given, we have 3 and 1. The fewest is 1. So our answer should only have 1 significant figure. So we're going to round to 1 radian per second. Okay, notice that the question says, the answer here says 1.2. That's because I should have put an extra 0 right here in the question, and then I would be rounding it to have 3 significant figures rather than only 1. All right, so I hope that helps. What we're doing here is basically just another inelastic collision, but it's rotational, so we have to look at the angular velocities. You have to, before you begin, think about which of the objects are particles and which of them are rigid bodies. So a rigid body is something that has actually like a size to it. A particle would be something really small in comparison. So we're treating the arrow like it's very tiny. We don't have any information about its size at all. So we're just going to treat it like it's a particle. The door, on the other hand, we're treating it like it's a slab, which is rotating about its end, just like where the hinges are located on a door, on its end. Okay, so that's why we're using those 2 different formulas. But I showed up above that those 2 formulas are basically the same thing. So if I use the moment of inertia of a particle, which is mr squared, then we end up getting the exact same formula anyways. The key to remember here is that the angle between the r vector and the velocity vector, if those 2 are perpendicular to each other, we don't really need to worry about this sine beta piece. Okay? Very rarely you will see that there is an angle between them, and that's when you have to put your sine beta in. Alright, I hope that helped. Thanks for watching.